Alright, so in this video we will be discussing renal tubular processing. तो first step is filtration, जिसमें plasma is filtered and plasma proteins and plasma bound substances remain back there. So plasma is basically plasma minus plasma protein plus plasma bound substances, and there is reabsorption through cells, then it's known as transcellular absorption. If it is between the cells, then it is paracellular absorption. Then steps to include secretion, which is actively done. So urine formation is basically the combination of three processes: glomerular filtration minus tubular reabsorption plus tubular secretion. Now let's move on to tubular reabsorption. We will focus on few basic principles of tubular reabsorption. So we know that GFR formed is 120 ml per minute, which is, if you want to calculate GFR formed in a total GFR of a total day, then it is total filter rate is equal to 120 into 1440, which is 60 into 24. Then we get it as around 172.8 liters per day of total filter rate is formed by both the kidneys, and only 1 ml is excreted as urine per minute. So we have 1440 minutes in complete day, so around 1440 ml is excreted, which is around 1.5 liter of urine excreted per day. So when we look at the filtrate and the excreted urine, maximum around 178.5 liter has been reabsorbed by the PCT tubules. Now let's focus on a basic thing before moving deeper. We have an active transport which is done against the concentration gradient and electrical gradient. It is of three types: primary, secondary. Primary is something which utilizes ATP directly, right? Secondary is something which utilizes the gradient created by the primary active transport. So it is secondary active transport. ATP is utilized indirectly. And penocytosis is something in which cell will engulf something, right? And energy is required in that process too. So now let's look at this. Okay, so if filtrate is formed, which is around 100 ml, right? And we are considering an approximate value. So if 100 ml of filtrate is formed, around 65% of water, sodium, everything is 65% of water and sodium are absorbed. Okay, and there is brush bordered epithelium which is present on the luminal side, and on the basolateral membrane we have a striated appearance due to mitochondria, which are required to supply energy to the sodium potassium ATPases. Alright, and now the sodium potassium ATPases, they push out 3 sodium out and 2 potassium in. In that way it makes the cell sodium poor. So the sodium channels, which are actually sodium glucose co-transporters present on the basolateral membrane, take up the sodium as there is a concentration gradient favoring inside, and while moving, when the sodium moves inside, it also takes up glucose along with it. So it is a sodium glucose co-transporter. And we talk about the sodium has been under facilitated diffusion due to concentration gradient, and glucose has entered through this transporter as in secondary active transport. And there when the potassium enters in, there are few potassium leaky channels through which sodium leaks out, and that's the reason it creates a electronegativity inside the cell, which also pulls up the sodium inside. So sodium moves inside due to concentration gradient and electrical gradient as well. Obein are the drugs which block the sodium potassium ATPases, and they stop the movement of glucose into the cell, right? Because when there is no gradient created by the sodium potassium ATPases, no sodium moves in and no glucose can be co-transported along with the sodium. Sodium potassium ATPases are important for making the cell sodium poor so that sodium can be reabsorbed. And when we look at this, there are tight junctions present between the two cells, and they allow free movement of water, right? And they keep the basolateral side and the luminal side and the basolateral side separate. Without letting the cell get inverted or anything, they fix their locations and they are leaky to water, right? They are not that tight. So, and there is another transporter called of sodium and amino acids, which transported sodium downhill and transported amino acids against the concentration gradient. So it's a secondary active transport of amino acid. And to facilitate diffusion, amino acids move out and then enter into the bloodstream. So amino acids are also absorbed 100%. Glucose is also absorbed 100%. And there is another transport of sodium and chloride, which transports the sodium downhill and chloride uphill. And chloride transport is secondary active transport. So chloride anyway can move into the interstitium directly, and what happens is at the end all these solutes, which are amino acid, glucose, sodium, everything gets accumulated in this interstitium, right? So these tight junctions are water permeable, right? So they pull up the water here, and in this way water is absorbed paracellularly. And when water flows paracellularly, few solutes are also present in the water and they get dragged along with the water. So this is known as solvent drag. Few solutes are also absorbed as a result of solvent drag. And early part of DCT takes sodium, glucose and amino acids, whereas late part of DCT is responsible for taking chloride. Body requires pH which has to be constant at 7.4. Slight fluctuation in pH will alter the protein configuration and result in enzyme dysfunctions, right? So body has to maintain a pH at 7.4. And we have a bicarbonates, and many acids are produced in body, and we have bicarbonates to neutralize those acids. So bicarbonates are constantly under threat of being destroyed, and we cannot afford to lose them. And no, for information, H plus concentration is around 40 nano equivalent per ml. Now, how does body preserve carbonate, which are filtered? So what happens is when the carbonate flows down, the acid release H plus. H plus combines with the carbonate and forms carbonic acid, which gets diffused to form water and carbon dioxide. Carbon dioxide is exhaled and water is lost or absorbed later. So this was a normal reaction that takes place, but body have to conserve carbonate. So what happens is water combines with the carbon dioxide. Carbon dioxide is usually present in every cell. Water combines with carbon dioxide to form carbonic acid by an enzyme called as carbonic anhydrase. This carbonic acid gets dissociated into carbonate and H+. This carbonate is reabsorbed by facilitated diffusion. This H+ is released out by sodium hydrogen exchanger. Okay, this takes sodium in and potassium out. Sodium moves in by facilitated diffusion, and potassium is moved against concentration gradient as a secondary active transport, and it is an antipode. Right, now this proton plus this carbonate combines to form H2CO3. This carbonic acid again dissociated into carbon dioxide plus water. This carbon dioxide is taken up in by facilitated diffusion, and carbonates are taken up, and this water is again absorbed later part. Right, in this way body preserves carbonate. And there is another transport of pinocytosis, which is also an active transport. This is for molecules like insulin, which is also filtered. They take up this low molecular weight insulin, and they are catabolized, and then amino acids are released. They can be taken up into the blood directly or might be used for gluconeogenesis. And in few pathological conditions, when there is an excess lysis of RBCs, hemoglobin are released directly into the blood as a tetramer. They break to form these dimers, and these dimers can be filtered through the glomerular filtration membrane, and these dimers are also taken up by the cells. They catabolize hemoglobin and iron is released. This iron will destroy the cells and cause acute tubular necrosis, and this is a complication seen in case of mismatch transfusions. So when we consider the absorption of glucose, So glucose is 100% absorbed in this PCT area. There is no glucose found in the loop of handling. If the filtered load of glucose increases, this machinery, these cells also increase their capacity to they can have a capacity to absorb glucose as much as it is increased in filtration. So there is something called as Tmax, which is also known as tubular absorption maximum. So when filtered load increases constantly, further increase will not be absorbed, then it appears in urine. Okay, if filtered load increases constantly, that it reaches to maximum point, which is around 300, that no nephron can absorb glucose completely after being at their high potential, then glucose start leaking into the urine. Okay, so sodium has no Tmax phenomena. It can go with chloride, glucose, amino acid by various co-transporters, and it can also be absorbed in principal cell too. So there is no concept of Tmax phenomena for sodium. And in the case of principal cells, there are sodium potassium ATPases, which can make the cell sodium poor, so that sodium can be dragged in by this sodium channels. And the sodium potassium ATPases are actively synthesized. Their synthesis is promoted by a hormone aldosterone. So sodium reabsorption depend on two things. One is a concentration gradient and electrochemical gradient. These two gradients are important, and it also depends upon time. So how this time is related? So when we consider the tubular fluid flow, if tubular fluid flow is fast, more GFR is and if there is more GFR, so there is a fast tubular flow, and there is less efficient absorption, right? Because fluid passes so quickly that cells cannot take up this complete sodium from it, so there is less contact time in this case. But if tubular fluid is slow, in case of low GFR, the contact time increases and more efficiently sodium can be absorbed. In that way, sodium reabsorption is time dependent, and glucose is reabsorbed independent of gradient and time.